Looking at another free response question, this one from back in 2003. This is a good one that has a nice mix of gas law and stoichiometry and theory. It's a good mixture, and so let's take a look. It also has a very important commercial chemical process. This is how iron ore, Fe2O3, that's iron 3 oxide, how that iron in the iron oxide is reduced to make iron metal in the refining process. So we have the 3+ iron ions gaining electrons to becoming iron metal, and the donator of those electrons, the reducing agent, is the carbon in the carbon monoxide, which goes from a 2+ oxidation state in the CO to a 4+ oxidation state in the carbon dioxide. So that's the process we're looking at, and they set this up by giving us a lot of information about the reactants. We have a 16.2 liter sample of the carbon monoxide, 1.5 atmospheres of pressure and 200 degrees C. So we have a volume, and we have pressure and temperature, so that is reeking of PV equals nRT. And then they also give us the mass of the iron oxide that we're going to start with too, 15.39 grams. So let's get busy with the numbers. First part is how many moles of carbon monoxide are available for the reaction. So we do have all that we need to calculate moles because we've got the volume and the pressure and the temperature. So we can solve for N in PV equals nRT. When we rearrange that equation, we're going to get N is equal to PV over RT, and plugging all of those numbers in with the gas constant being 0.0821 because we have atmospheres of pressure, and the temperature, of course, converting the Celsius to kelvins, making that 473 Kelvin. And when we plug those correct numbers into our PV equals nRT, we wind up with 0.626 mole of the carbon monoxide. Part 2, what's the limiting reactant for the reaction? And justify that with calculations. Well, we have the amounts now of both of the reactants because we've calculated the moles of carbon monoxide. So we got that. And they give us 15.39 grams of the iron oxide. So we know grams of our other reactant. We need to compare apples and apples, or oranges and oranges. So we have the moles of carbon monoxide, so let's convert those grams of iron oxide into moles. So we'll take our 15.39 grams and multiply that by the conversion factor, that is the molar mass of iron oxide. 1 mole over the molar mass, which is 159.7 grams. And that will give us the moles of Fe2O3, 0.0964. Now, we have obviously significantly more moles of the carbon monoxide, 0.6 compared to 0.096 for the iron. But we do have a 3-to-1 ratio in the stoichiometry, so let's prove our point, make sure we have the correct limiting reactant by doing a little stoichiometry with that mole-to-mole ratio and figuring out with our given amount of iron how much of the carbon monoxide would we need. So we set up that stoichiometry, the 0.964 mole of the iron oxide, the 3-to-1 mole-to-mole ratio of carbon monoxide and iron oxide. So our moles of iron oxide are going to cancel, and we wind up with how many moles of the carbon monoxide we need. And I'm running out of room. when we plug those numbers, we get 0.289 mole of carbon monoxide that is needed to react with the given amount of iron oxide that we have. So we need 0.289 moles. We have far more than that. We have 0.626 moles. So the carbon monoxide must be excess. That means the iron 3 oxide is the limiting reactant. In part 3 of part A, we want to know how many moles of iron metal, that's one of the products, is formed in the reaction. Well, again, this is some simple stoichiometry. We use our limiting reactant, which is the 0.0964 mole of the iron 3 oxide, and we use the 2-to-1 mole ratio of those two compounds, those two substances. So the stoichiometry looks like 0.0964 mole, and that's the Fe2O3, and we go 2-to-1 ratio, 2 Fe for every 1 Fe2O3, and so that will give us the moles of our iron that would be produced. And so it's just 2 times that quantity, 0.193 mole of Fe. That doesn't look much like an F. There we go. And so there's the first part all done. Part B has a little more stoichiometry and a bit of a limiting reactant problem, although I hope you'll be able to determine the limiting reactant without even doing a calculation. We have a reaction taking place in an aqueous solution where 0.6 mole of barium nitrate and 0.3 mole of phosphoric acid, H3PO4, are dissolved into 2 liters of water, which is going to come back and be important later. And so we are looking at a precipitation reaction here. We have barium phosphate, the solid forming, and we're also going to get nitric acid as a product, which is why they can ask this question. But since we haven't done our acid-base unit yet, we'll skip that for now. So calculate the mass of barium phosphate formed. Well, we know the molar amounts of both of the reactants, so we need to use the limiting reactant to start our stoichiometry. And the ratio in the balanced equation is 3 barium nitrates for every 2 phosphoric acids. So we need a 3-to-2 ratio, but we have 0.6 mole of barium nitrate compared to 0.3 moles of the phosphoric acid. So we need about 2/3 the amount of phosphoric acid compared to the amount of barium nitrate, but we only have about half that amount. We only have 0.3 moles of phosphoric acid compared to 0.6 moles of barium nitrate. So the H3PO4 must be the limiting reactant because we don't have as much as the stoichiometry says we need. So the phosphoric acid is going to be limiting. Now you can do the same kind of calculation we just did above. This is one of those problems where if you can see that relationship, you want to skip the math because they're not asking for that mathematical proof. Skip the math and just get on and do the stoichiometry. So we want the mass of barium phosphate that is formed, so we start with our 0.3 mole of the H3PO4, and we use the mole-to-mole ratio. We're going to get 1 of the barium phosphate for every 2 of our phosphoric acid. So our moles of phosphoric acid will cancel. Now we know moles of barium phosphate, and the second step, plugging in the molar mass of barium phosphate. And I'm running out of room, so I'm just going to tell you that molar mass is 602 grams per mole. And when we hitch that last bit into the equation and multiply through, we wind up with a value of 90.3 grams of barium phosphate as the product. That's the theoretical yield for that reaction. So skipping number 2, let's finish this up with number 3. What is the concentration in moles per liter, molarity, of the nitrate ion after the reaction reaches its completion? Well, we look back up at the formula for barium nitrate, which will be the source of the nitrate ions, and we see that there are 2 nitrates for every mole of barium nitrate. So since we dissolved 0.6 mole of barium nitrate into the solution, that would have been a total of 1.2 mole of nitrate ion, and that 1.2 moles of nitrate ion is dissolved in, importantly, that 2 liters of solution. So we're going to get 0.60 molar nitrate ions, and that is because the HNO3, that is the product there, is a strong acid, and thus all of those nitrate ions would be dissociated as NO3-, and obviously the H+ as well coming off of that acid. And that's it.